Tonight, as your head finds its place on the pillow, let your eyes wander to the window. There, beyond the glass, the night sky spreads like a vast, dark ocean. Each star is a tiny lighthouse, sending its ancient light across impossible distances to reach you here, in this quiet moment. You might think you're looking at emptiness between those stars. But you're not. You're looking at one of the universe's greatest secrets. Hidden in that darkness are worlds. Thousands upon thousands of planets, spinning silently around distant suns. Planets we call exoplanets. Worlds that exist beyond our solar system, in the deep spaces between the stars. Take a slow breath. Feel your body relaxing into the softness beneath you. As you breathe, imagine that each exhale carries your thoughts outward, beyond Earth's atmosphere, beyond the moon, beyond the familiar planets of our solar system. Your breath mingles with the cosmic wind, traveling to places where alien skies stretch over landscapes you've never imagined. Some of these distant worlds are scorching hot. Planets where molten rock rains from clouds of vaporized metal. Others are frozen solid, locked in eternal winter under the pale light of dying stars. But somewhere, in the perfect middle distance from their parent stars, some planets might be just right. Not too hot, not too cold. Places where water could flow like the streams and rivers you know on Earth. The ancient light reaching your eyes tonight began its journey long before you were born. Some photons left their star when your grandparents were children. Others started traveling when dinosaurs walked the Earth. This light has been crossing the universe for so long, carrying with it the secrets of worlds that existed in the distant past. But here's what fills scientists with wonder, and what should fill your dreams with possibility. We're not just guessing about these planets anymore. We found them. Real worlds, orbiting real stars, scattered throughout our galaxy like islands in an endless sea. The first exoplanet around a sun-like star was discovered in 1995. Since then, we've found thousands more. Each discovery is like opening a letter from the cosmos, written in the language of light and gravity. Some of these worlds are larger than Jupiter, gas giants that dwarf our Earth. Others are smaller than Mercury, rocky and mysterious. As your breathing slows and deepens, picture yourself as an explorer of the night sky. You don't need a spaceship or special equipment. Your imagination is the perfect vehicle for this journey. From your bed, you can travel farther than any human has ever gone. You can visit worlds where purple auroras dance in methane skies. You can walk on planets where crystalline mountains rise from seas of liquid nitrogen. The stars you see tonight are suns to countless worlds. Each point of light might warm the surfaces of planets where alien weather patterns swirl and flow. Rain might be falling on distant continents right now. Snow might be covering alien mountains. Storms larger than Earth itself might be raging in the atmospheres of gas giants, their winds howling across clouds that sparkle like jewels. And in some of those distant skies, clouds might be hiding something extraordinary. Something that could change everything we know about life in the universe. These aren't ordinary clouds made of water vapor like the ones that drift over Earth. These are alien clouds, formed from chemicals and compounds that barely exist on our planet. Some exoplanets have clouds made of tiny glass particles that would feel like silk between your fingers. Others have clouds of molten salt that glow like fire in their planet's twilight. Still others might have clouds so thick and dense that no light from their star ever reaches the surface below. But it's what might be hiding beneath these exotic clouds that keeps scientists awake at night, staring up at the same stars you see now. Because clouds don't just shape weather. They shape the possibility of life itself. They can protect a planet's surface from harmful radiation. They can trap heat and keep a world warm. They can carry water and nutrients across continents. Your eyelids are growing heavy now, but your mind can still wander among the stars. Think of all the worlds out there, spinning in the darkness, each one unique. Some have days that last for years. Others have nights that never end. Some planets are tightly locked to their stars, with one side always facing the light and the other trapped in eternal darkness. On one of these worlds, at this very moment, alien weather might be creating conditions perfect for life. Gentle rains might be falling on continents we'll never see. Seasons might be changing in ways we can barely imagine. And somewhere, beneath layers of protective clouds, the first stirrings of life might be taking their very first breath. The night sky holds all of these possibilities. Every star is a doorway to new worlds. Every distant sun might warm planets where life has found a way to flourish. As you drift toward sleep, you're connected to this vast network of worlds, all of them spinning through space together, all of them part of the same cosmic story. Tomorrow, scientists will point their telescopes at these distant stars, searching for the faint signals that reveal hidden planets. They'll study the light that filters through alien atmospheres, looking for clues about what lies beneath those exotic clouds. But tonight, as sleep approaches, you don't need telescopes or equations. You have something more powerful, the ability to dream of infinite possibilities among the stars. And as your consciousness begins to fade, as the boundary between waking and sleeping grows soft and blurred, you might wonder, how do we actually find these hidden worlds, scattered like cosmic needles in the vast haystack of space? As you sink deeper into comfort, your breathing steady and calm, imagine yourself as a cosmic detective. You're about to learn the most beautiful secret of modern astronomy. How do we find worlds that are trillions of miles away? How do we discover planets orbiting stars so distant that their light takes years to reach us? The answer lies in patience. And shadows. And the gentle art of watching. Picture a candle flickering in a dark room. Now imagine someone walking between you and that candle. For just a moment, the light dims. The person's shadow blocks some of the flame's glow. This simple idea, this brief blocking of light, is exactly how we find most exoplanets. Scientists call this the transit method. It sounds complicated, but it's beautifully simple. When a planet passes in front of its star, as seen from Earth, it creates a tiny eclipse. The star's light dims by the smallest amount. We're talking about changes so small that the star might dim by less than 1%. But our instruments are sensitive enough to notice. Your heart beats steadily in your chest. Each beat is regular, predictable. This is exactly what makes planet hunting possible. Planets orbit their stars in regular patterns, just like your heartbeat. If a planet crosses in front of its star once, it will do it again. And again. Creating a rhythm we can detect across the vast distances of space. The Kepler Space Telescope spent nearly a decade staring at the same patch of sky. It watched over 150,000 stars with unwavering attention. Like a patient gardener watching for the first signs of spring, Kepler waited for the telltale dimming that would reveal hidden worlds. And it found thousands of them. But stars don't just dim when planets pass in front of them. They also wobble. Imagine you're ice skating with a friend. You grab hands and spin together. Even though your friend might be smaller than you, they still pull you slightly off balance. You both orbit around an invisible point between you. This is exactly what happens with stars and planets. Every planet tugs on its star with gravity. Big planets create bigger tugs. The star wobbles back and forth, like a cosmic dance partner. We can measure this wobble by studying the star's light. When the star moves toward us, its light becomes slightly blue. When it moves away, the light becomes slightly redder. This shift is so small that it's like detecting the speed of a walking person from the other side of the country. Your muscles are relaxing now, letting go of the day's tension. In the same way, scientists have learned to let go of the need for perfect clarity. We can't see exoplanets directly, not yet. They are too small and too far away. Their light is drowned out by the blazing brightness of their parent stars. It would be like trying to spot a firefly sitting next to a powerful searchlight from hundreds of miles away. So instead, we've learned to read the signs. We've become detectives of starlight, finding clues in the tiniest changes in brightness and color. Sometimes, though, we get lucky. Sometimes we can actually take pictures of exoplanets. But only the largest ones, orbiting far from their stars. These direct images show us worlds that are nothing like the planets in our solar system. Young, hot planets that still glow with the heat of their formation. Gas giants larger than Jupiter, radiating infrared light into the cosmic darkness. There's another method that feels almost magical. It uses the bending of space itself. Einstein showed us that massive objects bend the fabric of space-time. When a star passes directly between Earth and a more distant star, it acts like a cosmic magnifying glass. The closer star's gravity bends and focuses the light from the star behind it, making it appear brighter. If that closer star has planets, they add their own tiny gravitational pull to the mix. For just a few hours or days, these planets create additional spikes of brightness in the background star's light. It's like seeing shadows cast by invisible objects, written in the language of bent starlight. Each method tells us different things about the worlds we find. Transit observations reveal a planet's size. How much light does it block? That tells us how big it is compared to its star. Wobble measurements reveal mass. How hard does the planet pull on its star? That tells us how heavy it is. Put size and mass together, and you can figure out what a planet is made of. Is it rocky like Earth? Gaseous like Jupiter? Or something in between? These basic facts help us understand whether a world might be capable of supporting life as we know it. Your breathing has slowed to match the rhythm of discovery. Each breath in brings new possibilities. Each breath out releases old assumptions about what planets can be. Because the worlds we found are stranger and more wonderful than anyone imagined. There are planets made of diamond, compressed carbon so dense that the entire world sparkles. There are planets where it rains glass sideways in 1,000-mile-per-hour winds. There are worlds where the surface is an ocean of lava, glowing red-hot under the light of a nearby star. And there are planets in the habitable zone. Worlds orbiting at just the right distance from their stars. Not too hot, not too cold. Places where liquid water could exist on the surface. These are the planets that make astronomers stay up all night, double-checking their data, hardly daring to believe what they found. But finding a potentially habitable planet is just the beginning of the mystery. Size and temperature only tell us so much. What we really want to know is what's happening in the atmospheres of these distant worlds. What gases surround them? What weather patterns shape their skies? And most importantly, what secrets might be hiding beneath their alien clouds? As sleep draws closer, you might find yourself wondering about those mysterious atmospheres, drifting like cosmic veils around worlds beyond counting, each one holding clues about the possibility of life in the universe. As your body settles into deeper rest, imagine the universe as a vast kitchen. In this cosmic kitchen, every star is like a stove, radiating heat into the space around it. Some stars burn hot and bright, like roaring campfires. Others glow gentle and warm, like cozy hearths on winter nights. Around each of these stellar stoves, planets orbit like dishes arranged at different distances from the heat. Some sit too close. These worlds are scorched and baked, their surfaces molten rock under the relentless glare of their nearby stars. Others orbit too far away, frozen solid in the cold depths of space, like forgotten meals left outside in winter. But somewhere in between, there's a special distance. Not too hot, not too cold. Just right. This is what scientists call the habitable zone, though many people know it by a more friendly name, the Goldilocks zone. Like the porridge in the famous fairy tale, planets in this zone have temperatures that are just right for something magical to happen. Liquid water can exist on their surfaces. Your breathing becomes slower and more rhythmic as you think about water. Water is life's most faithful companion. Every living thing on Earth depends on it. Your own body is mostly water, flowing through your veins, filling your cells, carrying nutrients and oxygen to every part of you that needs them. Water is picky about temperature. Heat it too much, and it becomes steam, drifting away into space. Cool it too much, and it freezes solid, locked away where life can't use it. But in the Goldilocks zone, water can remain liquid. It can flow in rivers, pool in lakes, fall as gentle rain. Our own Earth sits perfectly in the Sun's Goldilocks zone. We orbit at just the right distance to keep our oceans liquid and our atmosphere filled with the water vapor that creates our clouds and weather. If Earth were much closer to the Sun, our oceans would boil away. If we were much farther out, they would freeze solid. But here's what makes the search for exoplanets so exciting. Every star has its own Goldilocks zone. And we found planets orbiting in many of these habitable regions around distant stars. Some of these potentially life-friendly worlds orbit red dwarf stars. These stars are smaller and cooler than our Sun, so their Goldilocks zones are much closer in. A planet might orbit its red dwarf star in just a few weeks, racing around at a distance closer than Mercury is to our Sun. Yet because the star is cooler, temperatures on the planet's surface could still be just right for liquid water. Other exoplanets orbit stars similar to our Sun. These worlds might have years similar to ours, with seasons that change as they journey around their stars. Spring might bring warming temperatures and melting ice. Summer might see clouds forming over vast continents. Autumn might paint alien forests in colors we've never imagined. As your muscles relax and your mind grows quiet, picture one of these distant worlds. It's a rocky planet, about the same size as Earth. It orbits a star much like our Sun, at a distance that keeps its surface temperature mild and welcoming. On this world, morning might dawn over continents where rivers wind through valleys carved by millions of years of flowing water. The air might be thick enough to breathe, filled with gases that create weather patterns and seasons. Clouds might drift across skies that could be blue like ours, or perhaps tinted with different colors depending on what gases fill the atmosphere. But being in the Goldilocks zone doesn't guarantee that a planet will be habitable. It's just the first requirement, like having the right-sized pot before you can cook a perfect meal. Many other ingredients need to come together to create a world where life might flourish. A planet needs the right kind of atmosphere to trap heat and create stable temperatures. It needs protection from harmful radiation, perhaps from a magnetic field like Earth's invisible shield. It needs the right mix of chemicals and elements. And it needs time, lots of time, for complex processes to unfold. Some planets in the habitable zone might be covered entirely by oceans, with no dry land at all. Others might be mostly desert, with just small polar ice caps providing the only water. Still others might be locked in place, with one side always facing their star in eternal day, while the other side remains in permanent night. But each of these worlds represents a possibility. A chance that somewhere in the universe, water is flowing, weather is changing, and perhaps life is finding a way to exist and grow. The Goldilocks zone is like a cosmic invitation. It says, here, in this special distance from a star, the conditions might be right for something wonderful to happen. Here, chemistry and physics create the perfect stage for life's grand performance. Your heartbeat has slowed to match the patient rhythm of planetary orbits. Worlds circle their stars year after year, season after season, slowly changing and evolving. Some might develop thick atmospheres that trap heat and create greenhouse effects. Others might lose their atmospheres to space, leaving behind barren landscapes. The search for habitable exoplanets is really a search for worlds like ours. Places where water can flow, where chemicals can mix and react, where energy from a star can drive the complex processes that make life possible. And as you drift closer to sleep, you might wonder about the air that surrounds these distant worlds. What strange and wonderful atmospheres might blanket planets in the Goldilocks zone? What exotic gases might swirl in alien skies, creating weather patterns unlike anything we know on Earth? Take a slow, deep breath. Feel the air flowing into your lungs, filling your chest with life. The air you're breathing right now is a miracle of chemistry. Mostly nitrogen and oxygen, with tiny amounts of other gases mixed in like ingredients in a cosmic recipe. This invisible blanket surrounding Earth makes all life possible. But as you breathe in Earth's familiar atmosphere, imagine the alien airs that surround distant worlds. Each exoplanet has its own unique breath, its own signature blend of gases that tells a story about how that world formed and evolved. Some planets breathe hydrogen. These are often the largest worlds, gas giants that never developed solid surfaces. Their atmospheres are deep oceans of gas, stretching down for thousands of miles. If you could somehow stand in these hydrogen skies, you would sink like a stone through layers of increasingly dense gas, until the pressure would crush anything made of ordinary matter. Your breathing becomes steady and rhythmic as you picture these alien skies. On some worlds, the atmosphere is mostly carbon dioxide, thick and heavy like a blanket that traps heat from the planet's star. Venus in our own solar system has this kind of atmosphere. The air pressure there is so intense it would feel like being deep underwater, and the temperature is hot enough to melt lead. But carbon dioxide atmospheres don't have to be hellish. On cooler planets, carbon dioxide might create a gentle greenhouse effect, keeping the world warm enough for liquid water to exist. The gas might cycle through the atmosphere in great patterns, dissolving into oceans and then bubbling back out, creating a planetary breathing rhythm that lasts for thousands of years. Some exoplanets have atmospheres filled with water vapor. Imagine standing on such a world, where the air itself is thick with moisture. Every breath would taste of rain about to fall. The sky might be perpetually cloudy, with water droplets suspended in the air like a permanent, gentle mist. Lightning might flash constantly through these water-rich skies, splitting molecules and creating new chemicals with each electric spark. On worlds orbiting close to their stars, atmospheres can become truly exotic. The intense heat from nearby stellar fires can strip away lighter gases, leaving behind only the heaviest elements. Some of these planets might have atmospheres made of vaporized rock. Silicate particles could drift through their skies like metallic snow, condensing and falling as liquid stone rain when temperatures drop just enough. Your muscles are relaxing now, letting go of tension as you drift through these alien skies in your imagination. On colder worlds, far from their parent stars, methane takes the place of water in Earth's weather cycle. Methane clouds form in the frigid air. Methane rain falls on methane lakes. Methane ice covers the landscape in seasons that last for decades. Titan, Saturn's largest moon, gives us a glimpse of what such a world might be like. Its thick atmosphere is mostly nitrogen, like Earth's, but it's cold enough that methane acts like water. Rivers of liquid methane carve channels through icy landscapes. Methane storms rage across continents of water ice as hard as rock. But perhaps the most intriguing exoplanet atmospheres are the ones that might show signs of life. On Earth, oxygen is a rare and special gas. It reacts with almost everything it touches, so it doesn't last long in the atmosphere unless something is constantly producing it. That something is life itself. Plants and algae split water molecules, releasing oxygen as they capture energy from sunlight. If we could somehow analyze the atmosphere of a distant exoplanet and find oxygen mixed with water vapor and other gases, it might be the first hint that life exists there. The oxygen would be like a signature written across the sky, saying, "Something here is alive, something here is breathing, something here is changing the very air around it." Some planets might have atmospheres we can barely imagine. Worlds orbiting very close to their stars could have skies filled with glowing plasma, where the gas is so hot that electrons are stripped away from atoms. Other worlds might have atmospheres that change dramatically between day and night, with gases freezing out of the air on the cold side and evaporating back into the atmosphere on the warm side. Your breathing has synchronized with the imagined rhythms of alien weather. In and out, like the circulation of gases in a planetary atmosphere. Some exoplanets might have winds that circle the entire world, carrying heat from the day side to the night side. Others might have atmospheric layers that move in opposite directions, creating complex patterns of circulation that would make Earth's weather seem simple by comparison. The thickness of an atmosphere matters too. Some planets have air so thin you could barely detect it, wispy traces of gas that offer no protection from space radiation or meteorite impacts. Others have atmospheres hundreds of times thicker than Earth's, where the air pressure at the surface would be like being deep in our oceans. In these thick atmospheres, strange things can happen. Gases that would normally be invisible might become dense enough to refract light, creating optical effects like permanent rainbows or mirages that stretch across entire continents. Sound might travel differently too, with voices carried by the dense air over vast distances. As your consciousness begins to drift toward the edge of sleep, you might wonder about the weather patterns in these alien atmospheres. What kinds of storms rage in skies made of hydrogen and helium? How do seasons change on worlds where the atmosphere is mostly carbon dioxide? What would rain feel like if it were made of liquid methane instead of water? Temperature differences between day and night, between seasons, between the equator and the poles, all drive the movement of atmospheric gases. These movements create weather. And weather, over long periods of time, shapes the surface of a planet. It carves valleys, builds mountains of sediment, and spreads the chemical ingredients that life needs across entire worlds. But weather isn't just about gas moving around. It's also about particles suspended in that gas. Dust, ice crystals, tiny droplets of liquid, and sometimes stranger things. These particles gather together in the sky, forming structures that can hide entire worlds from view. And so, as sleep draws nearer, you might find yourself curious about those mysterious veils that hang in alien skies, wondering what secrets might be concealed beneath layers of clouds unlike any that drift across our familiar blue sky. As your body settles deeper into rest, let your mind drift upward like morning mist rising from a quiet lake. You're floating now through the cloud layers of distant worlds, where the sky itself tells stories written in droplets and crystals unlike anything that forms in Earth's familiar atmosphere. On Earth, clouds are mostly water. Tiny droplets suspended in air, or ice crystals that catch sunlight and paint our sky in shades of white and gray. But in the vast gardens of space, clouds can be made from almost anything that can condense from gas into liquid or solid form. Picture yourself drifting through the upper atmosphere of a gas giant orbiting a distant star. Here, clouds form from ammonia instead of water. These ammonia clouds stretch for thousands of miles, creating bands of color that wrap around the entire planet like ribbons on a cosmic gift. The clouds themselves might be white or yellow or brown, depending on what other chemicals mix with the ammonia as it condenses in the cold upper atmosphere. Your breathing becomes slow and steady as you imagine deeper cloud layers on this same world. Farther down, where temperatures are warmer, water clouds might form just like they do on Earth. But below those, in the deepest layers of the atmosphere, clouds made of liquid water droplets give way to even stranger formations. Here, sulfur compounds create clouds that would smell like rotten eggs if you could somehow breathe in this alien air. Some exoplanets have clouds made of materials that seem almost magical. On worlds where temperatures are just right, tiny particles of silicate dust can condense into clouds that sparkle like ground glass. These silicate clouds drift through alien skies like glittering fog, each particle a microscopic jewel catching starlight and scattering it in rainbow patterns. On other worlds, where pressure and temperature conditions are extreme, carbon itself can condense into clouds. Imagine floating through a sky where diamond dust drifts like snow. Each particle is a tiny crystal of pure carbon, harder than any material in your everyday world, yet light enough to float suspended in the alien atmosphere. Your muscles release their last traces of tension as you drift through these diamond cloud forests. The particles tinkle against each other with sounds too soft to hear, creating music from the collision of countless microscopic gems. Light from the planet star refracts through these carbon crystals, painting the sky in colors that have no names. But not all exotic clouds are made of solid particles. On some worlds, entire cloud layers consist of liquid droplets made from compounds that don't exist in liquid form on Earth. Clouds of liquid methane drift through frigid skies on planets far from their stars. Each droplet is like a tiny bubble of natural gas suspended in air so cold that your breath would instantly freeze solid. Other planets have clouds made from metals. On worlds that orbit very close to their stars, temperatures can be hot enough to vaporize iron, copper, and other metals. These metallic vapors rise high into the atmosphere, where they cool and condense into clouds that would look like drifting smoke made of liquid metal. When these metallic clouds release their rain, molten drops of iron and copper fall from the sky like a slow-motion fireworks display. As you float deeper into this meditation on alien weather, consider how these exotic clouds might affect any life that could exist on these distant worlds. Clouds don't just create pretty patterns in the sky. They shape entire planetary climates. On Earth, clouds help regulate temperature. White clouds reflect sunlight back to space, cooling the planet. But they also trap heat from the surface, like a blanket that keeps warmth from escaping into the cold of space. The balance between these two effects helps keep Earth's temperature stable enough for liquid water to exist. On exoplanets, exotic clouds might create very different climate effects. Diamond dust clouds might be incredibly reflective, bouncing most starlight back to space and keeping the planet's surface cool. But they might also be transparent to certain types of heat radiation, allowing the planet to warm up from below. Metallic clouds might conduct electricity, creating atmospheric circuits that generate powerful magnetic fields. These fields could protect the planet's surface from harmful radiation from space, the way Earth's magnetic field protects us. Or they might create spectacular aurora displays that paint the entire sky in shifting patterns of colored light. Your consciousness drifts now through cloud layers that change with the seasons on alien worlds. On planets with long, slow orbits, seasons might last for years or decades. Cloud patterns would shift gradually over these extended seasons, creating climate cycles that play out over time scales longer than human lifetimes. Some planets might have permanent cloud cover, thick enough that no direct starlight ever reaches the surface. These worlds would exist in eternal twilight, lit only by the soft glow that filters down through layers of clouds. But this doesn't mean they would be lifeless. On Earth, entire ecosystems exist in the deep ocean where no sunlight penetrates. Life finds ways to extract energy from chemicals instead of light. Beneath the permanent cloud cover of an exoplanet, similar chemical ecosystems might flourish. The clouds themselves might be part of the life cycle, carrying nutrients and energy sources from the upper atmosphere down to the surface, then carrying waste products back up to be recycled by atmospheric chemistry. But perhaps the most intriguing possibility is that life itself might exist within the clouds. On Earth, microorganisms have been found living in clouds, floating through the atmosphere and using the water droplets as their habitat. On exoplanets with thick, stable cloud layers, entire aerial ecosystems might evolve. Picture vast cloud forests in alien skies, where microscopic organisms drift through layers of mist and vapor. These aerial life forms might never touch solid ground. They could spend their entire life cycles floating in the atmosphere, feeding on chemicals dissolved in cloud droplets, reproducing in the gentle turbulence of atmospheric circulation. Such life would be almost impossible to detect from Earth. It would leave no footprints on the surface, build no cities, create no obvious signs of intelligence. These floating ecosystems would be hidden beneath layers of clouds, invisible to our telescopes, living secret lives in the skies of distant worlds. Your heartbeat has slowed to match the patient rhythm of cloud formation and dissipation. Clouds form when conditions are right, exist for a while, then fade away as atmospheric conditions change. This cycle of formation and dissolution might mirror the cycles of life itself on worlds where biology and meteorology intertwine. And as you drift on the edge of sleep, floating through these imagined cloud forests of the cosmic deep, you might wonder how we could ever hope to peer through such exotic veils to discover what lies beneath. What techniques might allow us to penetrate layers of diamond dust and metallic vapor to glimpse the surfaces of alien worlds, or to detect the subtle signs that life might be hiding in the clouds themselves? As you sink deeper into peaceful rest, imagine light as a messenger. Every photon that touches your closed eyelids has traveled an incredible journey to reach you. Some began their voyage at the surface of our sun just 8 minutes ago. Others left distant stars years, decades, or centuries before you were born. Each particle of light carries with it a story written in the language of color. When you were a child, you might have held a prism up to sunlight and watched it break apart into a rainbow. Red, orange, yellow, green, blue, indigo, violet. All the colors were always there, hidden inside what looked like pure white light. The prism simply separated them, spreading them out so you could see each color individually. This spreading of light into its component colors is called a spectrum. And it's how we read the messages that light carries across the universe. Your breathing becomes steady and rhythmic as you picture scientists doing the same thing with starlight that you did with that childhood prism. They collect light from distant stars and exoplanets, then spread it into rainbows. But these scientific rainbows are far more detailed than any you might see in the sky after a rainstorm. When astronomers create a spectrum from starlight, they don't just see smooth bands of color. They see dark lines cutting across the rainbow, like shadows interrupting the flow of light. These dark lines are where specific colors have been absorbed, stolen away by atoms and molecules that the light encountered on its journey. Each type of atom absorbs light at very specific colors. Hydrogen absorbs certain shades of red and blue. Oxygen takes away particular greens. Sodium steals a specific yellow. It's as if each element has its own unique fingerprint written in the language of light. When starlight passes through the atmosphere of an exoplanet, atoms and molecules in that alien air absorb some of the light's colors. By studying which colors are missing from the starlight we receive, scientists can figure out what gases exist in the planet's atmosphere, even though that world might be hundreds of light years away. Your muscles relax completely as you contemplate this cosmic detective work. It's like being able to taste a distant meal just by smelling the aroma that drifts to you on the wind. Except instead of scents carrying information about food, it's colors carrying information about the chemical composition of alien worlds. Water vapor in an exoplanet's atmosphere creates its own distinctive pattern of missing colors in starlight. Carbon dioxide has a different signature. Methane leaves its own unique fingerprint. Each molecule absorbs light in its own special way, creating a kind of barcode that scientists can read. But reading these cosmic messages isn't always easy. The signals are incredibly faint. Imagine trying to detect the scent of a single flower in a garden from miles away, while a powerful fan is blowing all the air in different directions. That's similar to the challenge of detecting the tiny changes that exoplanet atmospheres make to starlight. The atmosphere of an exoplanet might absorb only a tiny fraction of the light from its star. We're talking about changes of less than 1 part in 10,000. It's like trying to notice if someone removed a single grain of sand from a large beach. But our instruments have become sensitive enough to detect even these whisper-soft signals. And sometimes, when conditions are just right, we can detect more than just the presence of different gases. We can also learn about temperature, pressure, and even weather patterns in alien atmospheres. Different layers of an atmosphere have different temperatures. Hot gas absorbs light differently than cold gas. By studying how the absorption lines are shaped and shifted, scientists can create temperature maps of exoplanet atmospheres. They can tell which parts of an alien sky are hot and which are cold. Your heartbeat has synchronized with the patient rhythm of scientific observation. It takes time to collect enough light to create these detailed spectra. Telescopes must stare at the same star system for hours or days, gathering photons one by one, building up enough signal to overcome the noise. But the wait is worth it. These spectra can reveal the presence of clouds in exoplanet atmospheres. When light passes through clouds, it gets scattered and absorbed in different ways than when it passes through clear air. Scientists can sometimes tell not just that clouds are present, but what those clouds are made of. Water clouds scatter light differently than clouds made of sulfuric acid. Clouds of tiny rock particles create different spectral signatures than clouds of ice crystals. Each type of cloud leaves its own calling card in the light that eventually reaches our telescopes. Perhaps most exciting of all, these light-reading techniques might someday help us detect signs of life on distant worlds. If an exoplanet has oxygen in its atmosphere, that oxygen will absorb specific colors of light. The same is true for water vapor, carbon dioxide, and other gases that might be produced by living organisms. The combination of gases matters too. Finding oxygen and water vapor together in an exoplanet's atmosphere would be much more interesting than finding either gas alone. On Earth, these gases exist together partly because of life processes. Plants produce oxygen while using carbon dioxide and water. Animals do the reverse. If we could detect this same kind of chemical imbalance in an exoplanet's atmosphere, it might be our first hint that life exists there. The gases would be out of equilibrium in a way that suggests something is actively producing and consuming them, something that might be alive. Your consciousness drifts now like light itself, traveling across vast distances to touch alien worlds. Each spectrum is like a message in a bottle, thrown into the cosmic ocean by a distant planet and picked up by our patient telescopes after journeying for years through the void. As sleep draws nearer, you might find yourself wondering about all the messages we haven't yet learned to read. What other secrets might be hidden in the light from exoplanets? What stories are written in colors we haven't yet learned to decode? And what wonders might be concealed beneath clouds so thick that starlight never penetrates to the hidden oceans that might lie below? As your body settles into the deepest layers of rest, let your mind sink like a gentle current beneath the surface of imagined seas. But these aren't the familiar oceans of Earth. These are the hidden water worlds that might exist beneath the thick, cloudy atmospheres of distant exoplanets, places where vast oceans flow in eternal darkness, never touched by the light of their parent stars. Picture yourself descending through layers of alien clouds so dense that they block out all starlight. Down you drift, through kilometers of thick atmosphere, until suddenly you break through the bottom of the cloud layer. Below you stretches an ocean larger than any on Earth, its dark surface rippling with waves that have never known the touch of direct sunlight. This is what scientists call a water world. A planet where liquid oceans cover the entire surface, with no continents or islands breaking through the waves. The ocean might be hundreds of kilometers deep, containing more water than all of Earth's seas combined. And it exists in perpetual twilight, lit only by the faint glow that filters down through the planet's thick atmospheric blanket. Your breathing becomes as rhythmic as ocean waves as you imagine floating on this dark sea. The water might be warm, heated from below by the planet's interior, or kept liquid by the greenhouse effect of the thick atmosphere above. Or it might be cold, just barely above freezing, existing in liquid form only because of the immense pressure created by the weight of atmosphere pressing down from above. In our own solar system, we have hints of what such worlds might be like. Europa, one of Jupiter's moons, hides a vast ocean beneath its icy surface. Enceladus, orbiting Saturn, has geysers of water shooting up through cracks in its frozen shell. These hidden seas might contain more water than all of Earth's oceans, yet they remain completely separate from the vacuum of space, protected by layers of ice and rock. But the water worlds orbiting distant stars might be even more remarkable. Instead of being frozen on the surface like Europa, these exoplanets might have liquid oceans open to their atmospheres. Water could evaporate from the surface, rise into the atmosphere, condense into clouds, and fall back down as rain in a never-ending cycle. Your muscles release all tension as you drift deeper into this meditation on hidden seas. The rain falling on these water worlds might not be the gentle drops you know from Earth. Under different atmospheric pressures and in different gravitational fields, rain might fall as heavy droplets that create deep splashes. Or it might mist down like fog, so fine that the boundary between air and water becomes blurred. The chemistry of these alien oceans could be unlike anything on Earth. Our oceans are salty, filled with dissolved minerals that have washed down from continents over billions of years. But a water world with no land masses might have oceans with very different chemistry. The water might be pure, or it might be rich in chemicals that have bubbled up from the planet's interior or fallen down from the atmosphere. Some water worlds might have oceans that are slightly acidic, tinted with dissolved carbon dioxide from the atmosphere. Others might have alkaline seas, rich in dissolved minerals that would make the water taste bitter and strange. The color of these oceans could vary too. They might be the familiar blue of Earth's seas, or they could be green, red, or even purple, depending on what chemicals are dissolved in the water. As your consciousness drifts like a deep-sea current, consider what kinds of life might exist in these hidden oceans. On Earth, life thrives in the deepest parts of our oceans, in places where no sunlight penetrates. These deep-sea ecosystems depend not on photosynthesis, but on chemical energy. Bacteria near underwater volcanic vents use the chemical energy in hot, mineral-rich water to fuel their metabolism. Similar ecosystems might exist on water worlds. The ocean floors of these planets could be dotted with hydrothermal vents, places where hot water rich in dissolved minerals bubbles up from the planet's interior. Around these vents, entire ecosystems might flourish in the eternal darkness, fed by chemical energy instead of starlight. But life on a water world might not be confined to the ocean floor. The entire water column, from surface to bottom, could be filled with floating organisms. Without continents to provide nutrients through runoff, life would need to recycle materials within the ocean itself. Vast networks of floating organisms might create their own ecosystems, with some species producing food through chemosynthesis while others feed on them. Your heartbeat has slowed to match the deep, slow currents of these imagined seas. On Earth, ocean currents are driven partly by temperature differences between the equator and the poles, and partly by the rotation of the planet. Similar currents would flow in the oceans of water worlds, but they might follow different patterns. A water world with a very thick atmosphere might have surface temperatures that are nearly the same everywhere, from equator to pole. In such a world, ocean currents might be driven mainly by the planet's rotation, creating vast gyres that circle the globe. Or the currents might be driven by tidal forces if the planet has large moons, creating patterns of flow that change with the rhythm of celestial mechanics. These currents would be crucial for any life in the oceans. They would distribute heat, nutrients, and dissolved gases throughout the water. They might create upwelling zones where deep, nutrient-rich water rises to the surface, and downwelling zones where surface water sinks to the depths, carrying oxygen and other gases to the deep ocean. The seasons on a water world would be subtle but important. Even under a thick cloud cover, small changes in the amount of heat reaching the planet's surface could drive seasonal patterns in ocean temperature and chemistry. These seasonal cycles might trigger migrations of ocean life, breeding seasons, or changes in the distribution of nutrients. Some water worlds might have extreme seasons. If a planet's orbit is very elliptical, it might experience periods when it's much closer to its star and periods when it's much farther away. During close approaches, the ocean's surface might warm significantly, increasing evaporation and thickening the cloud cover. During distant periods, the surface might cool, and some of the water vapor in the atmosphere might condense and fall as torrential rains. Your thoughts flow now like gentle currents through these alien seas, carrying you toward the realization that such worlds might be among the most common types of planets in our galaxy. Rocky planets in the habitable zones of their stars, covered completely by water, shrouded in thick atmospheres that create eternal cloud cover. And as you drift on the edge of sleep, floating on imagined waves beneath alien skies, you might wonder how we could ever hope to detect the subtle chemical signatures that would tell us whether life exists in these hidden oceans, concealed beneath layers of cloud and atmosphere that block our view of the surface below. As you rest in perfect stillness, feel the gentle chemistry happening within your own body. Your heart beats with the rhythm of molecules flowing through your bloodstream. Oxygen travels from your lungs to every cell. Carbon atoms link together in long chains that form the proteins in your muscles. Nitrogen helps build the DNA that carries your genetic code. These same elements that make you alive exist throughout the universe. They drift between stars in cosmic clouds. They condense into planets around distant suns. They flow in the atmospheres and oceans of exoplanets scattered across our galaxy. The chemistry of life isn't unique to Earth. It's written into the very fabric of the cosmos. Carbon is life's favorite building block. This remarkable element can connect with itself and other atoms in countless ways, creating chains, rings, and complex structures that no other element can match. In your body right now, carbon atoms form the backbone of every protein, every strand of DNA, every molecule that makes your cells function. Your breathing slows as you contemplate the carbon cycle that connects you to the stars themselves. The carbon in your body was forged inside ancient stars that lived and died billions of years ago. When those stars exhausted their fuel, they scattered their carbon-rich ashes into space. That carbon drifted through cosmic clouds until it eventually became part of the disk of material that formed our solar system. On distant exoplanets, carbon follows similar paths. It might exist as carbon dioxide in thick atmospheres, creating greenhouse effects that keep water liquid on planetary surfaces. It might dissolve in alien oceans, providing raw material for complex chemistry. Or it might form organic molecules in the clouds themselves, creating the chemical foundation for life processes we can barely imagine. Oxygen brings energy to life's chemistry. When you breathe, oxygen molecules in your lungs combine with carbon in your blood, releasing energy that powers every function of your body. This same partnership between oxygen and carbon could drive metabolism on worlds orbiting distant stars. But oxygen is a restless element. It reacts with almost everything it touches. In the atmosphere of a lifeless planet, free oxygen would quickly disappear, combining with rocks and metals until none remained in the air. The fact that Earth's atmosphere contains so much oxygen is actually proof that life exists here. Plants and algae constantly produce oxygen through photosynthesis, replacing what gets consumed by chemical reactions. Your muscles relax completely as you think about this delicate balance. If astronomers detect free oxygen in the atmosphere of an exoplanet, it might be the first sign that life exists there. Something would have to be constantly producing that oxygen to keep it from disappearing. That something could be life itself. Nitrogen completes life's essential trio. It's a key ingredient in amino acids, the building blocks of proteins. It's also crucial for DNA and RNA, the molecules that store and transmit genetic information. Nitrogen gas makes up most of Earth's atmosphere, providing a vast reservoir that life can tap into when needed. On exoplanets, nitrogen might play similar roles. Dense nitrogen atmospheres could provide stable, relatively inert environments where more reactive chemistry can take place. Lightning in nitrogen-rich skies could create chemical reactions that produce organic compounds, just as it does in Earth's atmosphere. The dance of these elements creates endless possibilities for chemistry throughout the universe. Hydrogen, the simplest and most abundant element, can combine with carbon to form hydrocarbons. Add oxygen, and you get alcohols and organic acids. Include nitrogen, and you can build amino acids and nucleic acids. Throw in phosphorus and sulfur, and you have all the elements needed for the complex chemistry of life. Your heartbeat has synchronized with the slow rhythm of cosmic chemistry. These reactions don't happen quickly. They unfold over thousands, millions, or billions of years. But given enough time, simple molecules can grow into complex structures. Amino acids can link together to form proteins. Nucleic acids can arrange themselves into genetic codes. Scientists have found organic molecules in space itself. In the cold, dark regions between stars, carbon compounds drift in cosmic clouds. These molecules are simple by biological standards, but they're the same building blocks that eventually became part of living things on Earth. They suggest that the raw materials for life are common throughout the galaxy. Meteorites that fall to Earth sometimes contain amino acids and other organic compounds. These space rocks carry chemistry that formed in the early solar system, preserving a record of the chemical processes that were happening billions of years ago. The same processes are likely happening around other stars right now, as new solar systems form and evolve. Water acts as the perfect stage for life's chemistry. It dissolves many different substances, allowing them to mix and react. It remains liquid over a wide range of temperatures. It can break apart and reform chemical bonds, facilitating the complex reactions that life requires. Most importantly, water is stable. Unlike many other solvents, it doesn't break down easily under the conditions where life might exist. On exoplanets in the habitable zones of their stars, water could serve the same crucial role. It could dissolve carbon compounds, nitrogen molecules, and phosphorus-containing chemicals, creating rich chemical soups where life's processes could begin. The chemistry would be similar to what happened on early Earth, but the details might be wonderfully different. Your consciousness drifts now through cosmic laboratories where chemistry experiments have been running for billions of years. Each exoplanet is a unique test tube with its own combination of elements, temperatures, pressures, and energy sources. Some experiments fail, creating sterile worlds where chemistry never progresses beyond simple compounds. But others succeed, building complex molecules that eventually learn to reproduce and evolve. The elements that make life possible are abundant in the universe. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are all common products of stellar nucleosynthesis. They exist in the atmospheres and crusts of rocky planets. They dissolve in alien oceans. They participate in atmospheric chemistry driven by starlight and lightning. This abundance gives scientists hope. If the building blocks of life are common throughout the galaxy, then life itself might not be as rare as we once thought. Every star system could be running its own chemistry experiments, testing different combinations of elements under different conditions. And as you drift toward the peaceful realm of sleep, you might wonder how we could ever detect the subtle chemical signatures that would reveal whether these cosmic experiments have succeeded in creating life on distant worlds hidden beneath layers of alien clouds. Take a slow, deep breath. As you exhale gently into the quiet night, you're adding oxygen to the air around you. But you're also doing something more profound. You're participating in one of the most important chemical signatures of life on Earth. Every breath you release carries the invisible message that our planet is alive. This oxygen in our atmosphere is what scientists call a biosignature. It's a calling card that life leaves behind, a chemical fingerprint that can only exist when living things are present. Without plants, algae, and other photosynthetic organisms constantly producing oxygen, our atmosphere would contain almost none of this life-giving gas. Your breathing becomes steady and rhythmic as you consider how remarkable this is. Oxygen is so reactive that it would disappear from our atmosphere in just a few million years if nothing was replacing it. The fact that our air contains 21% oxygen tells a powerful story. It whispers to anyone who knows how to listen, life is here. On distant exoplanets hidden beneath layers of alien clouds, similar biosignatures might be waiting to be discovered. Each world conducting its own chemistry experiments, each potentially developing its own unique ways of announcing that life has taken hold in the cosmic darkness. But oxygen isn't the only calling card that life might leave behind. Living things are chemical factories, constantly taking in simple molecules and transforming them into more complex compounds. In the process, they often produce waste gases that accumulate in their planet's atmosphere. On Earth, life produces many different gases. Methane bubbles up from swamps and is belched by cattle. Hydrogen sulfide rises from hot springs and decomposing organic matter. Dimethyl sulfide drifts up from the oceans, created by tiny marine organisms. Each of these gases tells part of the story of our living world. Your muscles relax completely as you imagine the subtle chemical symphony playing out in Earth's atmosphere right now. Millions of species are breathing, photosynthesizing, decomposing, and metabolizing. Each biological process adds its own notes to the atmospheric composition, creating a complex mixture that could only exist on a world teeming with life. Scientists are learning to read these chemical signatures like a cosmic language. They study how different combinations of gases might indicate the presence of life on distant worlds. It's not enough to find just one biosignature gas. Life's fingerprint is written in the relationships between different atmospheric components. For example, finding oxygen and water vapor together in an exoplanet's atmosphere would be much more interesting than finding either gas alone. On Earth, these gases coexist because of photosynthesis. Plants split water molecules, releasing oxygen into the air while using the hydrogen to build organic compounds. This process creates a chemical signature that's hard to explain without biology. Even more compelling would be finding oxygen alongside gases that normally react with it. Methane and oxygen, for instance, react with each other and disappear from the atmosphere unless something is constantly replenishing both gases. On Earth, life produces both oxygen through photosynthesis and methane through various biological processes. Finding this unlikely combination on an exoplanet might be our first hint that life exists there. Your heartbeat has slowed to match the patient rhythm of atmospheric chemistry. These biosignature gases don't appear overnight. They build up slowly over thousands or millions of years as life establishes itself and begins to modify its planet's atmosphere. The search for these signatures requires the same patience that life itself demands. Some biosignatures might be completely alien to us. Life on other worlds might have evolved different biochemistries that produce gases we haven't thought to look for. Perhaps alien organisms use sulfur compounds instead of oxygen for their metabolism. Maybe they produce exotic gases that don't exist in Earth's biosphere. This possibility both excites and humbles scientists. We might discover atmospheric signatures that clearly indicate the presence of life, but life so different from our own that we struggle to understand how it works. These alien biosignatures could teach us that biology is far more creative and diverse than we ever imagined. The seasonal cycles of biosignature gases could also tell us about life on distant worlds. On Earth, the concentration of carbon dioxide in our atmosphere changes with the seasons as plants grow and die, absorb and release this gas. Similar seasonal variations in an exoplanet's atmosphere might indicate the presence of large-scale biological processes. Imagine detecting the rhythmic breathing of an entire planet as its biosphere inhales and exhales with the changing seasons. the atmospheric composition would shift subtly but measurably, creating patterns that could only be explained by the coordinated activities of countless living organisms. Your consciousness drifts now through imagined atmospheres where life has left its chemical fingerprints. Some worlds might have subtle biosignatures, barely detectable traces of gases that hint at hidden ecosystems. Others might have dramatic atmospheric signatures, where life has so thoroughly transformed the air that its presence is undeniable. The clouds that shroud these distant worlds might actually help preserve biosignature gases. Thick atmospheres can protect delicate molecules from being destroyed by ultraviolet radiation from their parent stars. Cloud layers might act like cosmic umbrellas, allowing life's chemical signatures to build up over geological time scales. But detecting these faint signals across interstellar distances remains one of the greatest challenges in astronomy. The atmosphere of an exoplanet might contain only tiny amounts of biosignature gases. Separating these weak signals from the noise created by the planet's star, its clouds, and our own instruments requires extraordinary precision and patience. Future space telescopes will be designed specifically to hunt for these elusive signatures. They'll study the light filtering through exoplanet atmospheres, looking for the telltale absorption lines that indicate the presence of oxygen, methane, water vapor, and other potential biosignature gases. The search might take decades. We might analyze hundreds of exoplanet atmospheres before finding one that shows clear signs of life. But every negative result will teach us something valuable about the conditions required for life to emerge and thrive. As sleep begins to embrace you, your own breathing becomes part of Earth's ongoing biosignature experiment. Each exhale adds to the oxygen content of our atmosphere, maintaining the chemical balance that announces our planet's living status to the cosmos. And in your dreams, you might wonder about the extraordinary tools that astronomers are building to peer through alien clouds and decode the atmospheric messages that distant worlds are sending across the vast darkness of space. As you rest in the peaceful darkness of your room, imagine floating in the cold silence of space, 1.5 million kilometers from Earth. Here, where the gravitational pulls of Earth and Sun balance perfectly, hangs one of humanity's most remarkable creations. The James Webb Space Telescope drifts in eternal orbit, its golden mirrors gleaming like a technological flower blooming in the cosmic void. This telescope is larger than your bedroom. Its primary mirror stretches 6.5 meters across, made of 18 hexagonal segments that fit together like a golden honeycomb. Each segment is coated with a layer of gold so thin that if you could hold it, it would be nearly transparent. Yet together, these mirrors collect infrared light with a sensitivity that surpasses anything humans have ever built. Your breathing slows to match the patient rhythm of cosmic observation as you picture this mechanical marvel at work. Unlike telescopes on Earth that must peer through our planet's turbulent atmosphere, Webb floats in perfect vacuum. No air currents disturb its view. No weather clouds its vision. It stares into the depths of space with unwavering attention, gathering ancient photons that have traveled for billions of years to reach its golden mirrors. The telescope's vision extends far beyond what human eyes can see. While your eyes detect only visible light, Webb sees in infrared wavelengths, the same kind of radiation you feel as heat from a warm fire. This infrared vision allows it to peer through cosmic dust clouds that would completely block visible light. It can see the birth of stars in dusty stellar nurseries, the formation of galaxies in the early universe, and most importantly for our journey, the hidden atmospheres of distant exoplanets. Webb's location in space is as carefully chosen as its design. It orbits at what scientists call the second Lagrange point, a gravitational sweet spot where it can maintain a constant position relative to Earth and Sun. From this vantage point, it can observe any part of the sky for extended periods, accumulating the faint light needed to study the most distant and subtle cosmic phenomena. Your muscles relax completely as you contemplate the engineering marvel that makes Webb's observations possible. The telescope must be kept incredibly cold to detect the faint infrared glow from distant objects. A 5-layer sunshield, each layer thinner than human hair, protects the mirrors and instruments from the heat of the sun. This sunshield is larger than a tennis court when fully deployed, creating a shadow that keeps the telescope's sensitive components at temperatures approaching absolute zero. When Webb studies an exoplanet atmosphere, it performs a cosmic magic trick. It doesn't actually see the planet directly. Instead, it watches as the planet passes in front of its star, blocking some of the star's light. By comparing the light before, during, and after this transit, Webb can detect the tiny fraction of starlight that has passed through the planet's atmosphere. This filtered starlight carries within it the chemical fingerprints of whatever gases exist in that distant atmosphere. Water vapor absorbs certain infrared wavelengths. Carbon dioxide absorbs others. Methane, oxygen, and dozens of other molecules each have their own unique signatures written in the language of infrared light. The precision required for these measurements is almost incomprehensible. Webb must detect changes in starlight of less than 1 part in 10,000. It's like being able to notice if someone removed a single grain of sand from a vast beach, or detecting the dimming of a lighthouse caused by a moth flying in front of it from hundreds of miles away. Yet Webb achieves this precision routinely, night after night, as it surveys the atmospheres of distant worlds. Your heartbeat has synchronized with the slow, methodical pace of space-based astronomy. Each observation requires careful planning and execution. Webb's instruments must be pointed with extraordinary accuracy, its mirrors must remain perfectly aligned, and its detectors must operate at the limits of physical possibility. Yet it performs these feats while floating in the vacuum of space, farther from Earth than the Moon. The telescope's discoveries are already revolutionizing our understanding of exoplanet atmospheres. It has detected water vapor in the skies of gas giants orbiting close to their stars. It has measured temperature differences between the day and night sides of tidally locked planets. It has even begun to characterize the atmospheres of smaller, rocky worlds that might be more similar to Earth. Each spectrum Webb obtains is like a message from another world, written in the universal language of light and chemistry. These messages tell stories of alien weather patterns, of chemical cycles unlike anything on Earth, of worlds where glass rains sideways and metals condense into clouds. They speak of planets where the very air might shimmer with exotic compounds that exist nowhere in our solar system. But perhaps most exciting are the hints of what Webb might discover in the coming years. As it studies smaller and smaller exoplanets, it edges closer to the possibility of detecting biosignature gases in alien atmospheres. The telescope has the sensitivity to detect oxygen, methane, and water vapor in the atmospheres of Earth-sized planets orbiting nearby stars. Such a discovery would represent one of the most profound moments in human history. Your consciousness drifts now alongside this robotic explorer, sharing its patient vigil in the cosmic darkness. Webb operates continuously, its golden mirrors collecting photons while most of humanity sleeps. It works through our nights and days, accumulating data that will take scientists years to fully analyze and understand. The telescope represents the culmination of decades of human ingenuity and international cooperation. Engineers from multiple countries contributed to its design and construction. Scientists from around the world compete for observing time on its instruments. Its discoveries belong not to any single nation, but to all of humanity, expanding our cosmic perspective and our understanding of our place in the universe. Even as you rest, Webb is likely observing. Perhaps it's studying the atmosphere of a super-Earth orbiting a red dwarf star. Maybe it's analyzing the complex chemistry of a hot Jupiter's upper atmosphere. Or it could be attempting one of its most challenging observations, searching for signs of water vapor around a small, rocky planet in its star's habitable zone. The telescope's mission will continue for at least a decade, possibly much longer if its systems remain healthy. During that time, it will study hundreds of exoplanet atmospheres, building a comprehensive catalogue of alien air compositions. Each new spectrum will add to our understanding of how planets form, how atmospheres evolve, and how common the conditions for life might be throughout our galaxy. As sleep draws you deeper into peaceful rest, you might find yourself wondering about the challenges that even Webb's extraordinary capabilities cannot overcome, and about the future discoveries that might teach us whether we are alone in the universe. As you settle deeper into the quiet embrace of sleep, imagine yourself as a cosmic detective faced with the most challenging mystery in the universe. You're searching for signs of life among the stars, but the evidence is often as elusive as shadows dancing on water. Not every signal you detect tells the story you hope to hear. Sometimes, the cosmos plays tricks on even our most sophisticated instruments. Picture a scientist studying the spectrum of light from a distant exoplanet. the data shows what appears to be oxygen in the planet's atmosphere. Hearts race with excitement. Could this be the first detection of life beyond our solar system? But then, after months of careful analysis, the truth emerges. The oxygen isn't being produced by alien plants. Instead, it's created when ultraviolet light from the planet's star breaks apart water molecules in the upper atmosphere. Your breathing becomes steady and peaceful as you contemplate how often nature creates false hopes in our search for life. The universe is full of processes that can mimic the chemical signatures we associate with biology. What scientists call false positives are like cosmic mirages, appearing to show us oases of life where none actually exist. Clouds themselves can be master deceivers. Dense cloud layers can hide the true composition of a planet's lower atmosphere, where life would most likely exist. A planet might have a rich, oxygen-filled atmosphere near its surface, but if thick clouds of water vapor or other compounds shroud the world, our telescopes might never detect the biosignature gases below. We might dismiss a living world as sterile simply because its life remains hidden beneath an impenetrable veil. Sometimes, the deception works in reverse. Clouds can create spectral features that look remarkably similar to the absorption lines we expect from biosignature gases. Water ice crystals high in an atmosphere might absorb light at wavelengths very close to those absorbed by oxygen or methane. Without extremely careful analysis, scientists might mistake these cloud signatures for signs of life. Your muscles relax completely as you consider the patience required for this cosmic detective work. Each potential biosignature detection must be studied from every possible angle. Scientists must rule out all non-biological explanations before they can claim to have found evidence of life. This process can take years, involving multiple observations with different instruments and countless hours of analysis. Volcanic activity can create some of the most convincing false alarms. On Earth, volcanoes release sulfur compounds, carbon dioxide, and water vapor into the atmosphere. These same gases might be produced by life processes on other worlds. A planet with active volcanism might appear to have biosignature gases in its atmosphere, but the source would be geological rather than biological. Even more challenging are the seasonal variations that geological processes can create. On some planets, the changing distance from their star during an elliptical orbit might drive cycles of volcanic activity. As the planet moves closer to its star, tidal forces increase, triggering more volcanic eruptions. As it moves farther away, volcanic activity decreases. These cycles could create patterns in atmospheric composition that mimic the seasonal changes we might expect from biological processes. The search for biosignatures is like trying to identify birdsongs in a forest full of rustling leaves, creaking branches, and flowing water. Each natural sound can mask or mimic the specific patterns you're listening for. Only by understanding all the possible sources of noise can you learn to distinguish the authentic songs from the false ones. Your heartbeat has slowed to match the methodical pace of scientific verification. Good science requires skepticism, especially when the stakes are as high as discovering life beyond Earth. Every claimed detection must be scrutinized by multiple independent research teams. Every possible alternative explanation must be considered and tested. Weather patterns on exoplanets can create their own misleading signals. Imagine a world where massive storms redistribute gases throughout the atmosphere in regular cycles. These atmospheric circulation patterns might create temporary concentrations of certain gases that appear and disappear in ways that seem biological but are actually meteorological. Cloud formation itself follows patterns that can fool our instruments. On planets with complex weather systems, clouds might form and dissipate in rhythmic cycles that create periodic changes in how much starlight reaches different parts of the atmosphere. These changes could affect the spectral signatures we detect, creating apparent variations in atmospheric composition that have nothing to do with life. The history of exoplanet science is filled with discoveries that later proved to be instrumental artifacts or misinterpretations of data. Early detections of exoplanet atmospheres sometimes turned out to be caused by starspots on the host star or by contamination from Earth's own atmosphere. Each false alarm taught scientists valuable lessons about the pitfalls of remote atmospheric analysis. Technology itself can create phantom signals. Tiny imperfections in telescope mirrors, subtle electronic noise in detectors, or unexpected interactions between different components of an observing system can all produce features in spectra that look like atmospheric absorption lines but actually originate from the instruments themselves. Your consciousness drifts now through this landscape of uncertainty and careful verification. The search for life requires not just advanced technology, but also the wisdom to recognize when that technology is leading us astray. Scientists must become experts not only in what biosignature gases should look like, but also in all the ways those signatures can be faked by non-biological processes. This challenge makes genuine discoveries all the more precious. When scientists finally do detect a combination of atmospheric gases that can only be explained by biological processes, when they've ruled out every possible false positive and confirmed their results with multiple independent observations, that moment will represent one of the greatest achievements in human history. The patience required for this work mirrors the patience of evolution itself. Life took billions of years to develop on Earth, gradually changing our planet's atmosphere in ways that are now unmistakable. The search for similar changes on distant worlds requires the same kind of long-term commitment and careful observation. As sleep draws you into its gentle embrace, you might find yourself wondering about the future of this cosmic search, and whether tomorrow's discoveries will finally reveal clear, undeniable evidence of life hiding beneath the alien clouds that veil so many distant worlds. As you drift on the gentle currents between waking and sleeping, let your mind travel forward through time to a future where the search for life among the stars has reached extraordinary new heights. Tomorrow's astronomers will possess tools that make today's most advanced telescopes seem like simple magnifying glasses held up to the infinite cosmos. Picture telescopes so large they cannot be built on Earth. These future observatories will float in the cold vacuum of space, their mirrors stretching hundreds of meters across. Some will consist of multiple smaller telescopes flying in perfect formation, their light combined by computer precision to create virtual mirrors larger than football fields. These space-based arrays will collect light with a sensitivity that will make the faintest whispers from distant worlds audible across the galaxy. Your breathing becomes deep and steady as you imagine the revolutionary techniques these future instruments will employ. They will not merely analyze the light that passes through exoplanet atmospheres during transits. They will actually block out the blazing light of distant stars, creating artificial eclipses that reveal the planets orbiting in their shadows. For the first time, we will see exoplanets directly, tiny points of light that carry their own stories written in reflected starlight. These direct observations will transform our understanding of alien worlds. Instead of inferring the presence of clouds from subtle changes in spectral absorption lines, future astronomers will watch weather patterns evolve on distant planets in real time. They will observe storms larger than Jupiter's Great Red Spot raging across alien skies. They will track the seasonal formation and dissipation of cloud systems on worlds orbiting stars dozens of light-years away. The technology needed for these observations is already being developed in laboratories around the world. Engineers are designing space telescopes that can measure the positions of their components to within fractions of the width of an atom. They are creating new types of detectors that can count individual photons and determine their exact colors with unprecedented precision. They are building computer systems that can process the vast amounts of data these observations will generate. Your muscles release all tension as you contemplate the patient international cooperation these projects will require. Future space telescopes will be too complex and expensive for any single nation to build alone. Scientists from dozens of countries will contribute their expertise, just as they do today with projects like the James Webb Space Telescope. The search for life will unite humanity in a common scientific quest. Within the next few decades, these advanced instruments will begin their systematic survey of nearby star systems. They will study every potentially habitable planet within 50 light-years of Earth, creating detailed atmospheric profiles for hundreds of worlds. Some will prove to be sterile, their atmospheres shaped only by geological and photochemical processes. But others may reveal the unmistakable chemical signatures of life. The first confirmed detection of biosignature gases on an exoplanet will mark a watershed moment in human history. The discovery will likely come not from a single dramatic observation, but from years of careful study by multiple telescopes. Scientists will detect oxygen and water vapor in perfect chemical balance, or methane and oxygen coexisting in impossible equilibrium, or perhaps entirely new atmospheric signatures that can only be explained by alien biology. That discovery will spark the next phase of exploration. Once we know that life exists on a particular world, we will turn our most powerful instruments toward detailed study of that planet's biosphere. We will map the distribution of different gases across its surface. We will search for seasonal variations that might indicate large-scale ecological cycles. We will look for signs of complexity that might suggest not just life, but intelligent life. Your heartbeat has synchronized with the slow rhythm of cosmic discovery. Each new technique will open windows into aspects of alien worlds we can barely imagine today. Future telescopes will detect the glow of city lights on the night sides of distant planets. They will measure the reflective properties of alien vegetation. They will even search for artificial atmospheric signatures, industrial pollutants that might indicate technological civilizations. The clouds that currently hide so many exoplanet secrets will become transparent to these advanced observations. Future instruments will peer through multiple layers of alien atmospheres, from the highest clouds down to planetary surfaces. They will create three-dimensional maps of atmospheric composition, revealing how different gases are distributed at different altitudes and latitudes. Some of the most exciting discoveries may come from studying planets that are completely unlike Earth. Future telescopes will analyze the atmospheres of super-Earths with crushing surface pressures and mini-Neptunes with exotic chemical compositions. They will study tidally locked worlds where one hemisphere bakes in eternal daylight while the other freezes in permanent night. Each type of planet will teach us something new about the conditions where life might arise and thrive. Artificial intelligence will play a crucial role in these future discoveries. Machine learning algorithms will sift through vast databases of spectral observations, searching for subtle patterns that human scientists might miss. AI systems will identify candidate biosignatures in real time, alerting astronomers to the most promising targets for follow-up study. They will even help design observing strategies that maximize the chances of detecting signs of life. Your consciousness floats now through imagined futures where the question of life beyond Earth has been definitively answered. Perhaps we will discover that simple life is common throughout the galaxy, but complex multicellular organisms are rare. Or maybe we will find that intelligence arises frequently once life gains a foothold on a world. Each possibility will reshape our understanding of our place in the cosmic community. The search itself will continue to evolve and expand. Future generations will build telescopes capable of studying planets around the nearest stars in extraordinary detail. They will develop new techniques for detecting life that we haven't yet imagined. They may even find ways to communicate across interstellar distances with civilizations that share our curiosity about the universe. But perhaps the most profound impact of these future discoveries will be on humanity itself. Learning that we are not alone in the universe will fundamentally change how we see ourselves and our planet. It will unite us in the recognition that Earth is just one example of a phenomenon that occurs throughout the cosmos. It will inspire new generations of scientists, philosophers, and explorers to continue pushing the boundaries of human knowledge. As sleep finally claims you, carrying you gently into dreams of alien skies and distant worlds, you rest with the knowledge that tomorrow's discoveries are already taking shape in the minds and laboratories of today's visionaries, preparing to reveal secrets that have been hidden in the cosmic darkness since the universe began.